In the last lecture, we have seen how the complex combinational circuits can be designed using fundamental circuits. These fundamental circuits mean we have considered half adder, full adder, the decoder. Now, today we will read how the combinational circuits can be designed using another fundamental circuits called multiplexer. Now, already we have read the functions of multiplexer, but again quickly we revisit that thing. So, how we have defined a 2 to 1 multiplexer? It has 2 input line and 1 select line. Now, function is that if the inputs are passed to the output depending on the particular value of the select line input. That means, if the Z is I0, that means I0 is passed to Z when S0 is 0. Similarly, when I1 is passed to Z, that means Z equal to I1 if S0 is 1. Now, if we consider a 4 to 1 multiplexer, 4 to 1 means that 4 input 1 output. Now, here we have to select 4 lines, that means either Z equal to I0, Z equal to I1, Z equal to I2 and Z equal to I3. So, I need 4 combinations of select lines, and if it is 4 combinations, then I need at least 2 select lines. 2 select lines. So, it will be 0 0 0 1, that means my S0 S1 values are 0 0 0 1 1 0 1 1. So, for these 4 combinations, that I0, I1, I2 and I3 will be passed to Z. So, in general what we can tell, that number of data inputs is 2 to the power n and number of control input is n. Control input means our select lines. So, this is my select lines should be S0, S1 up to Sn. Then my number of data inputs is I0, I1, I2, then I 2 to the power n minus 1. So, here actually S should be in such lines. So, it will be S0 to Sn minus 1, S0 to Sn minus 1, and for that n values it will be input should be 2 to the power n number of inputs, means 0 to 2 to the power n minus 1. So, just now what we have seen, this is for my 4 variable inputs or 4 to 1 multiplexers. 4 to 1 multiplexers, that S should be 2 lines or n equal to 2 and I equal to 2 square 2 to the power n equal to 2 square equal to 4. So, just the earlier slide what we have told, that if S1 is 0 0, then my output, this is my output Z, that will be I0, if it is 0 1, output is I1, if it is 1 0, output is I2, if it is 1 1, output is I3. So, earlier we have read only 2 to 1 multiplexer, 4 to how 4 to 1 multiplexer can be designed, again using 4 to 1 how I can design 8 to 1 multiplexer, all these things. Now, today we will see first the general structure. So, if now we draw the general diagram, then this will be my n control inputs, these are my control inputs and these are my primary inputs. So, for S0 to Sn minus 1 means n control inputs, primary inputs should be 2 to the power n and only one output. Now, that 4 to 1 multiplexer using 2 to 1 multiplexer, we call this is a Mux tree or multiplexer tree. This is in general called the Mux tree, or sometimes it is called the hierarchical design of Muxes. This is the hierarchical design. So, we take 2 to 1 multiplexer and it is fed to another 2 to 1 multiplexer. So, for 1 4 to 1 multiplexers we need 4 inputs I0, I1, I2, I3 this, and 2 control inputs, they are actually hierarchically fed. In the first level, this is my level 1, here the control input is S0 for both the 2 to 1 multiplexer. In the second level, this is my level 2, here S1 is fed. So, these are the 2 control variables or the control variables, 2 bit control variable. So, when S0 is 0, I0, I2 get selected in the first level, and when S0 is 1, then I1, I3 get selected at the first level. So, if S0 equal to 0, this become the 0th, I0, I2 0th and the first inputs to the next level. Now, at the next level mean the second level, the input output determined by the rest of the bits of their index after stripping of the LSB. So, now if I want to design a general architecture using multiplexer, then actually we have to consider the multiple levels. So, in the just now what we have seen, we have level 1 and level 2. So, this is my level 1 and this is my level 2. So, in the first level I0, I2 is fed, and in the second level again in the first level I1, I3 these are fed to 2 2 to 1 multiplexer. So, here S0 equal to 0. So, when S0 equal to 0, this is when S0 equal to 0, then I0, I2 is passed to the second level input. When S0 equal to 1, then I1, I3 is passed to the second level. Now, in the second level there are 2 inputs. See here, this is my 2 inputs I0 and I1. So, these 2 inputs are the output of the first level. These are the output of first level, and this is my output Z, final output Z. So, S1 is the control input and that can be 0 or 1. So, if it is 0, Z equal to I0, if it is 1, Z equal to I1. So, if I summarize that thing, that Z equal to, for the Z equal to I0 of level 2 when S1 equal to 0, when S1 equal to 1, Z equal to I1. Okay. So, the design works as a 4 to 1 multiplexer. Now, if I apply the same thing for constructing a 8 to 1 multiplexer. So, we can write that design of 8 to 1 mux. Now, for 8 to 1 mux, there are 8 inputs, primary inputs are 8, that is I0 to I7. So, my 2 to the power n equal to 8. So, n is n equal to 3. So, I need 3 control inputs. So, in this way I define my or I choose how many control lines will be there or how many select lines will be there. So, 8 inputs I0 to I7 and there are 3 select lines. Now, if I want to design 8 to 1 multiplexer using smaller multiplexers, say 2 to 1 or 4 to 1, then as 8 to 1, if I use 2 to 1 multiplexer, so I need 4 such multiplexers because I have 8 inputs. So, these I have given as for each 2 to 1 multiplexer I have given 2 inputs I0 I1 for the first one. This is my number 1 multiplexer. This is my number 2 multiplexers where I2 I3 is there. For 3 this is I4 I5, for 4 this is I6 I7. So, I0 to I7 primary inputs are applied for 4 2 to 1 multiplexer. Now, I got actually these are the first level outputs. So, these are my first level output which will be treated as the second level inputs. As there are 4 outputs, so I am at the second level I am taking a 4 to 1 multiplexer. Now, already we have seen the how 4 to 1 multiplexer can be designed using 3 2 to 1 multiplexer. So, this 4 to 1 multiplexer can be replaced by 3 2 to 1 multiplexers. Then it will be a hierarchical thing. First 4 2 to 1, then 2 2 to 1, then 1 2 to 1 multiplexer. That is also another alternative design of the 8 to 1 multiplexer. Now, this second level, here these are the first level outputs, actually these are Z0, Z1, I can tell this is Z0, Z1, Z2, Z3, that first level output, they are treated as the second level input. So, these are also first level output, they are also the second level input. These are also the second level input. Then they are fed to a 4 to 1 multiplexer. Now, here 4 to 1 we know that 4 primary inputs and 2 control lines. So, and So, this will be one output, that is my Z output. So, in this way I can design. So, if I see that general design, now if we generalize this design structure. So, generalize, I have n control lines, n control inputs, then 2 to the power n primary inputs, it is fed to a 2 to the power n to 1 multiplexer. How I can design that thing in a hierarchical structure? So, 2 to the power n, so I need that n number of or 2 to the power n minus 1 number of 2 to 1 multiplexer. Why? See, I have 2 to the power n input, 2 to the power n primary inputs. Now, 2 to the power n can be written as 2 into 2 to the power n minus 1. So, instead of applying 2 to the power n to at a time the primary inputs, these are 2 to the power n, what I can do, these I can replace by say 2 to the power n minus 1 number of 2 to 1 multiplexer, where every multiplexer has 2 inputs. So, this will be 2 into 2 to the power n minus 1. Now, in the next step what we can do, that 2 to the power n minus 1, that can be written as 2 into 2 to the power n minus 2. So, in that way I can replace the circuits. See, here the 2 to the power n primary inputs, they are replaced by 2 to the power n minus 1 number of 2 to 1 multiplexer. So, here there will be 2 to the power n minus 1, 2 to the power n minus 1, here it was 2 to the power n number of primary inputs, where it will be 2 to the power n minus 2 to the power n minus 1 number of primary inputs. Now, this is a 2 to the power n minus 1 to 1 multiplexer. Even if I want another hierarchical structure here, then in that way the 2 into 2 to the power n minus 2 or 2 into 2 to the power n minus 3, in that way I can design that hierarchical tree or the multiplexer tree. So, what we can conclude from here, that using this 2 to 1 multiplexer or using this 2 to 1 multiplexer, any large multiplexer circuit, any large multiplexer can be designed. So, hierarchical design of 2 to 1 multiplexer is possible. So, now we want to concentrate that the today's topic, that how the combinational circuits, any combinational circuits can be designed using this multiplexer. Because just now what we have seen, that any larger multiplexer can be designed using the smallest or the fundamental multiplexer 2 to 1 multiplexers. So, if now we any combination circuits we can realize using multiplexer, then obviously that design structure has some regularity, that using this multiplexer only I can, the whole circuit can be designed. First we take one simple example. say I have a 3 variable function, 3 variable function f where the min term exists in the function is 0 to 6, 7. So, min terms are 0, 2, 6 and 7. Now, how we can map this thing to a multiplexer? See that ABC we can define, if ABC we define as the 3 select lines or the control inputs. If it is a 3 select lines, then the multiplexer will be 2 to the power 3, means that 8 to 1 multiplexer, primary inputs will be 8. And if it is a, we know that if it is a 3 variable function, 3 variable function, the number of min terms. So, for 3 variable function, number of min terms are 8. So, the number of variable we can take the, or we can map the number of variable as the control lines or control input, number of control inputs, control lines or control inputs. So, in this case it is S0, S1, S2, that is my ABC. And the primary inputs, number of primary inputs will be the 2 to the power number of variables. So, in this case it will be 2 to the power 3. So, ABC has the control inputs for 8 to 1 multiplexer, and the data inputs are I0 to I7, because already we have seen this is 2 to the power 3 equal to 8 primary inputs, 8 PIs, and these are the possible min terms of f. So, the decimal equivalent of the primary inputs, that represents my min terms. So, input II or the primary input is a min term, and that number appears in the notation f. So, that means I want to design a multiplexer whose, if I want to design a multiplexer that it has 3 input lines, say these are my S0, S1, S2, and 8 primary inputs I0 to I7, and only my z equal to 1, means the z or output will, it will give the output for the primary inputs, that I0 to I7, these values will be, the decimal equivalent will be that 0, 2, 6 and 7, means these values will be all 0, 0, this value will be 2, then 6, then 7. So, only for these values that output will be 1. So, if that particular II is a min term of f, it is connected to a 1, otherwise it should be connected to a 0. So, just now what we have used, so this is my 3 select lines, A, B, C. These are my this S0, S1, S2, and these are my primary inputs. That means, when these primary inputs take the value, my primary inputs take the value 0 in decimal, then it will be that f will be 1. Or what we can tell that, say for pi equal to one of the pi values are 0 to 6, 7. So, for which value of ABC these pi values will be taken, because this is my variables, these are my variables. So, for 0 0, say for we know that if my select lines are 0 0 0, then I 0 will be passed to 1. So, this is my I 0 which is kept as 1. Then 2 means it is 0 1 0, then my Z is, that is my Z, this is I 2 which is kept as 1. If it is 6 means 0 or 1 1 0, this is 1 1 0, then I 6 is 1, it is 1 1 1, then I 7 equal to 1. That means, only these values when passed. For the rest of the values, that means, say for 0 0 1, for 0 1 1 3, 1 0 0 4, 1 0 1 5, for these 4 values my output Z is 0. That means, I 1 equal to 0, I 2, I 3 equal to 0, I 4 equal to 0, and I 5 equal to 0. So, this marks, this 8 to 1 multiplexer is nothing but the realization of the function of m sigma m 0 to 6 7. So, these combinational circuits, what we can tell, that the combinational circuit, that a 3 variable combinational circuits f a b c is sum of m, min terms are 0 to 6 7, that is nothing but a 8 to 1 multiplexer. This is 8 to 1 multiplexers, where these values are ABC, 3 select lines, and the output, this will be the only these 0 to 6 7 lines are 1, in these inputs are 1. That means, this is 0, this is 1, 3 line is 0, 4 line is 0, 5 line is 0, 6 line is 1 and 7th line is 1. So, this is the realization using multiplexer. See, only the decimal equivalent of the min terms, that particular min term, and that is mapped to the decimal equivalent of the primary inputs, and that particular min terms, which min term exists in the function, I have to keep that particular input as 1, because only for that for this marks that particular input will be passed to the output as 1. So, for the same example, if we see the general design rule, what we will be doing that we take that a 3 variable function 0 to 6 7, then select any 2 variable a b for the 2 control inputs. Now, earlier I have taken the 3 variables as the control inputs. Now, in a 3 variable Carnot map, group together squares into 2 squares in which the other variable c varies, but a b remains constant. So, form the implicants 2 square only within 2 squares and write out the function. See, here I have taken a 3 variable function, where the uh, 0 to 6 7 that values are there. That means that my function is f of a b c, and same example that 0, 2, 6 and 7, only that min terms will be there. So, this is my Carnot map realization. See, this is 0. So, this is my 0, this is my 0 1 0 means 2, this is my 1 1 0 means this is my 6, this is 1 1 1 7. So, what will be the function? Function will be a bar, b bar, c bar, then a bar, b, c bar, and this is my see, if I group together, this is one couple and this will be my a b. So, this is my a b. This is my, actually this is a bar, b bar, c bar, this is a bar, b, c bar. And see which one is a b bar. See, a b bar is this one, this is totally 0. That means, what I am doing, if I take the, I want to design these combinational circuits using a multiplexer. So, for this multiplexer, I know that earlier what we have seen, that all the 3 variables I have made that 3 variables as the control inputs or the select lines. Now, I want that only 2 variables are the control inputs. So, if AB are the control inputs, then if it is a multiplexer, AB are the control inputs, then it will be either 0 0. So, these are my AB 0 0 0 1 1 0 1 1. See, so these are my values, means that which represents the columns. This is 0 0 0 1 1 0 1 1. Now, 0 0 means only C bar exists. So, this is my, so actually what I can tell, this is my I 0 term, A bar B bar means 0 0. For 0 0, this is my I 0 term. See, this is my I 1 term 0 1, 0 1 means second column, A bar B. So, this is my I 1 term. A B bar means that actually fourth column, A B bar is the fourth column. So, that is my I 2, and this is A B means 1 1, this is my I 3. Now, see what is my I 0, I 1, I 2, I 3? When A B is 0 0, I 0 is nothing but C bar, I 2 is, I 1 is also C bar, I 2 is 0 because my fourth column is empty, I 3 is 1. So, that 3 variable actually I have changed 2 as the control lines and 1 as the primary input. So, if we see the design, so the what will be my design rules? Function will be in terms of combinations of A B ANDed with either C bar 1 or 0. What we have seen, that this is my C bar 0 and 1. Here there is no C term or a C bar. So, actually 0 1 and the other primary input left, that will be treated as the primary input of the multiplexer, and the two A B lines are the treated as the select lines. So, we will connect either C bar 1 0 to the data input or the primary input corresponding to the A B combination. They are ANDed with the expression for F. So, already we have seen this is my function if we want to realize that using multiplexer, that 4 to 1 multiplexer implementation, because there are two, I have selected two control lines or select lines, and so for 2 control lines there will be 4 inputs, 4 primary inputs, they are C bar 0 1. So, this is my design. So, this is my design of that of F equal to zero to six 7 or okay, we can tell that just now what design we have seen, that A B are the two select lines and the primary inputs are C bar, primary inputs are C bar, that means when a b equal to 0 0, then also c bar will be passed to f. When a b equal to 0 1, then also c bar will be passed to f. So, this is c bar 0 1. So, general n variable function implementation possible using a 2 to the power n to 1 multiplexer, because this is a 4 to 1 multiplexer without using extra gates. So, always this implementation is possible. So far what we have discussed, that if it is a n variable function, that what we can do, that all n variables we can take as the select lines, that will select a particular input, primary input to be fed to the output. Now, the minterms which present in the combinational circuits, only for that minterm or the binary of that minterms which fed to the select lines, then that particular input will be kept or will be applied as 1, and all other terms which are not the minterms of that combination circuits, they are kept as 0. So, that multiplexer will realize that particular combinational circuits. Now, in this current example what we have seen, even we can reduce that control signals. What we have done, that in this case, that for n variable we have taken a n minus 1 select lines, and the primary input is replaced by 0 1 and the complement and uncomplemented input which is left. So, in this way what we can do, that we can optimize that design, that select lines, we can divide the number of variables sum as the select lines and the combinations of some of the input variables as fed to the primary inputs. Now, we see if how we can do a larger design. So, 4 variable design using multiplexer. See, this is one example where the function is one combination of circuits we are taking, or the function is a bar b bar c bar d bar, a bar b bar c d bar, a bar b c bar, or actually this term is not there, a bar b c, or what we can tell that number of we can define this function as, this is one example where this is a 4 variable function a, b, c, d, and the minterm exists are, see this is 0 0, that means 0 is there. See, this is 1 0, this is actually it is shifted, this is 1 0 0 0, means my 8. Then for the second row, this is 1 0 0 1, this is 9. Third row, this is 0 1 1 1, 7. For the fourth row, it is 0 0 1 0, means 2, and this is 0 1 1 0, means 6. So, these 6 minterms are there. So, this is one combination circuits I want to realize using multiplexer. So, first what we do, again if I say first I see what is my minterms available. See, this is my A bar B bar C bar D bar. So, this is my A bar B bar C bar D bar, this one. Then A bar B bar C D bar, which one is that? A bar B bar C D bar. So, this one is A bar B bar C D bar. Then A bar B C bar 0 means see my third column is empty. Third column is empty means that there is no CD term. Or there is no AB term also, we can tell. Now, A bar B C 1, this is my, that second one is A bar B C, A bar B, and this is this, for this couple this is A bar B C, and this is D is 1. C exists, D is not there. So, A bar B C. Now, similarly we can write the, we can represent this function like this. So, now what we can do, that if I take, first thing what we can do, that for AB, the ABCD, the 4 variable can be taken as the select lines. Then it will be a 2 to the power 4 to 1 or 16 to 1 multiplexer. Now, I want to optimize this thing. So, we have taken ABC at the 3 select lines. Now, if ABC at the 3 select lines, then and D at the, D should be my, D can be my one of the input variables, that means D, D bar and 0, 1, this can be my input variables. And what we can do, that ABC, there are 8 combinations. So, the functions, the function f I am writing in terms of these 8 possible combinations of ABC. So, this is A bar B bar C bar D bar, which is my this one. A bar B bar C D bar, A bar B bar C D bar means this is my this one. Now, next row, this is A bar B. Now, A bar B means this A bar B C D. Okay. So, A bar B C D means this particular one, and A bar B C D bar means this particular one, and D plus D bar is 1, means there is no D term exists there, and this is also A bar B C 1. So, if I take together, this is my A bar B C, this is my A bar B C. Now, A B bar C bar, A B bar means if I take this one, this couple, then this will be my A B bar C bar, which is this term. A B bar C 0, this is not there, then A B C bar 0, it is not there, and A B C this is A B bar, A bar B bar, A B C 0 means A B, this is my that third column is not there, third column full A B is 0. So, this term is not there. So, now if I see that which combinations of ABCs are there, see now I write the 3 select lines ABC. These are 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. What are the terms? Say this is my A bar B bar C bar. This is my A bar B bar C. This is my A bar B C bar, A bar B C, A B bar C bar. This is my A B bar C. This is my A B C bar, and this is my A B C. Now I see which are there. For A bar B bar C bar, D bar is there, and for A bar B bar C D bar. So, for these two it is C C bar, this is D bar. So, for this my output should be D bar, and for this my output should be D bar. See, for A bar B C bar, output should be 0, and A bar B C output is 1. So, A bar B C bar output is 0, A bar B C output is 1. Then A B bar C bar and A B bar C 1 0. A B bar C bar 1, A B bar C 0. Then A B C bar and A B C 0 0. Then A B C bar and A B C, this is 0 0. So, now these 8 will be my primary inputs, D bar 0 1 1 0 0 0, and for these combinations 0 1 1 0 0. That means, if I draw, if I draw that circuit, that what will be the thing, that these will be D bar, these will be my D bar, and D bar 0 1 1 0 0 0. So, these will be my 8 inputs, and that 3 ABC are the combination. This is my 8 to 1 marks, this is my 8 to 1 multiplexer, and which realizes this particular function. So, in this way I can design any combinational circuit to using multiplexer. Either ABCD all can be select lines, and just in this example what we have seen, that we have reduced the select lines by 1. We have taken among the 4 variables, we have taken 3 as the select inputs, and the input are treated as the 0 1 combinations of 0 1 and d and d bar. For this particular example, there is no d exist, only d bars are there. So, in this way we can design the any variable n variable combination circuits using multiplexers. So, this is my general 4 variable this is my design rule, that for 4 variable design using multiplexers. So, we take that the quiz question for this lecture, that realize the following 4 variable function using multiplexers, and the function is z is a bar b bar c d bar plus a b bar c d bar plus a bar b bar c bar d bar plus a b bar c d bar plus a b c d. So, today what we have discussed, the design procedure, the design rules, using that we can design this thing. So, we will end the today's lecture here. Thank you. So, we are discussing how we can design the combinational problems or complex combinational problems using fundamental circuits like decoder, multiplexer, adders, etc. Last day we have discussed how we can design combinational circuits using multiplexer, the generalization of that design. Today we will see some large problem design, but before that we continue some the 4 variable design that we are discussing in the last class. So, 4 variable design using muxes. Last day what we have seen, that in general a 2 to the power I to 1 mux, where I less than n minus 1 can be used to implement an n variable function. So, that n variable is 0 to n minus 1 by choosing any I variables, means that if I have a function f n, say n number of variables a 0, a 1 up to a n minus 1, then first what we have discussed, that a multiplexer where that n number of select lines can be used to realize this function. Then always it is possible to design this function